One of the biggest questions in science and philosophy is, are we alone in the cosmos? You might think this is a question that has fascinated humanity for centuries, and that we are actively searching for signs of life beyond Earth. But why does the search for life seem like an afterthought? Astronomers search the heavens for years and years and years, and what they choose to look at seems counterintuitive to finding life. If we take a step back and look at this from the macro perspective, it almost seems like there's an intentional reason to look everywhere but where life may be. And I wonder why. What do astronomers look at most of the time? It depends on what field of astronomy they specialize in. There are many different fields of astronomy, such as solar astronomy, planetary astronomy, stellar astronomy, galactic astronomy, extragalactic astronomy, and cosmology. Each field focuses on a different aspect of the universe and requires different tools and techniques to study it. For example, solar astronomy studies the sun and its effects on the solar system. They use telescopes that can observe the sun in different wavelengths of light, such as visible, ultraviolet, and X-ray. They also use spacecrafts that orbit around the sun or fly close to it to measure its magnetic fields or solar wind and flares. Planetary astronomers study the planets, moons, asteroids, and comets in our solar system and beyond. They use telescopes that can track the motions and orbits of these objects. They also use spacecrafts that fly or land on these objects and take pictures and collect samples, such as Mars, the Moon, Venus, and in the future some moons of Jupiter or Saturn. Galactic astronomers study the Milky Way galaxy and its structure, formation, and history. They use telescopes that map the distribution of stars, gas, and dust in our galaxy. They also use telescopes that can detect the radio waves emitted by hydrogen atoms, which trace the spiral arms of our galaxy. Extragalactic astronomers study other galaxies beyond our own, and their properties such as shape, size, mass, distance, and evolution. Cosmologists study the origin, structure, and fate of the entire universe. They use telescopes that can observe the cosmic microwave background, radiation, or CMB, which is the leftover heat from the Big Bang. If you follow science, you've seen this one a million times about this model. But as you can see, astronomers look at a variety of things in the universe depending on their interests and goals. The focus, while spread out over different fields, is really narrowed to structure, i.e. how things work or were formed, and while beneficial to our understanding of the universe and physics, is still so narrowed down at the big questions. The real question, outside of where did this universe come from, the one that most people are interested in, is, are we alone in the universe, or is there life elsewhere? And if you look through all these forms of research, this question seems mostly void. If anything, they will sometimes suggest they are looking for extremely benign signs of biological life. But how much do they care about finding life? How much effort do they put into searching for signs of biological activity or intelligence among the billions of stars and planets out there? How much money do they spend on building instruments or launching missions that could detect or communicate with extraterrestrial beings? The answer is, not much. Don't get me wrong, there are some astronomers who are very passionate about finding life in the universe. There are some projects that are dedicated to this goal, for example, SETI, the search for extraterrestrial intelligence. SETI uses radio telescopes or optical telescopes to scan the sky for artificial signals that can indicate technological activity or communication. And SETI has been going on for decades. And its one anomalous signal it detected, the WOW signal, was basically overlooked and forgotten about. We pointed our instruments back at that point in time and found no other signal, so it's just noted as a weird anomaly, no consideration that it might have been possibly from an alien craft that was moving, thus the originating location of the signal has moved. Next up is TESS, the Transiting Exoplanet Survey Satellite. It's a NASA mission that searches for planets around nearby stars using the transmit method. TESS monitors the brightness of stars and looks for tiny dips that occur when a planet passes in front of them, blocking some of their light. TESS has 4 wide-field cameras that can cover 85% of the sky and observe more than 200,000 stars over 2 years. TESS is expected to find thousands of exoplanets, including many that are Earth-sized or smaller and orbiting in the habitable zones of their stars. TESS also provides prime targets for further characterization by other telescopes, such as the James Webb Telescope. TESS is an impressive mission that has already made many exciting discoveries. For example, it has found a marshmallow world, a planet that is about half the size of Neptune and has a very low density, suggesting that it has a thick atmosphere or a large ocean. It has also found a planetary system with a second Earth-sized world, a planet that is spiraling to its doom around its star, and a planet that orbits two suns like Tatooine from Star Wars. But how much does TESS help us find life in the universe? Well, it depends on how you define life and what kind of life you're looking for. TESS is designed to find planets that are potentially habitable, meaning they could have temperatures and pressures that could allow liquid water to exist on their surfaces. Liquid water is considered a key ingredient for life as we know it on Earth. However, liquid water alone does not guarantee life, nor does it tell us anything about the complexity or diversity of life that might exist on these planets. To find out if these planets actually have life, we need to look for biosignatures, which are chemical or physical indicators of biological activity or processes. For example, oxygen in the atmosphere could be a biosignature if it is produced by photosynthesis. However, oxygen could also be produced by non-biological processes, such as photolysis or volcanism. Therefore, we need to look at multiple biosignatures that are consistent with each other and rule out false positives. TESS itself cannot detect biosignatures directly, of course, because it only measures the brightness of stars and not their spectra. Spectra are the fingerprints of light that reveal the chemical composition and physical properties of objects. To detect biosignatures, we need telescopes that can measure the spectra of exoplanet atmospheres and look for specific molecules or features that indicate life. This is where James Webb Telescope comes in. It is a giant infrared telescope that was launched and is able to observe some of the planets found by TESS in more detail. We performed transmission spectroscopy on a few planets, with the initial findings being, well, inconclusive. But James Webb will also use a technique called direct imaging, and it takes pictures of exoplanets directly without being blinded by their stars. And it's challenging because exoplanets are very faint and close to their stars compared to our instruments' resolution and sensitivity. It will use a device called a coronagraph, which blocks out most of the starlight and reveals the fainter planets around it. By using these techniques, James Webb will be able to study some of the most promising exoplanets found by TESS and look for biosignatures such as water vapor, carbon dioxide, methane, ozone, and oxygen. We will also be able to study other aspects of exoplanets such as their climates, weather patterns, seasons, and surface features. However, it will have its limitations. James Webb will only be able to observe small fractions of the planets found by TESS, because not all of them will be suitable for transmission spectroscopy or direct imaging. It will also have a limited lifetime of about 10 years and a limited observing time that will be shared among many other scientific goals. And again, this is where I come into prioritizing, where how much time is allotted for people actually observing these very limited ways of finding life. From most of the stuff reported, it really seems like most of the time is dedicated to staring into black holes or neutron stars. When it does look at exoplanets, we invest all our study into planets orbiting around red dwarfs, where they're both tidally locked, being so close to the sun, but also extremely unlikely to have an atmosphere due to the intense flaring from red dwarfs. Meaning, it was seen from one perspective, an intentional looking for life in a place where there should be none, rather than trying to look at systems and exoplanets that favor life more from what we understand. What we need is more telescopes in the future that can complement and extend the capabilities of TESS and JWST. But it's not just that. Why is it that only one James Webb and TESS telescopes were built? Why do we build one-offs that may easily get damaged or destroyed when deploying? Wouldn't it make more sense, even from a redundancy aspect, to create two of them, allowing for a failsafe? And if both survive, you've now doubled your capability to research the cosmos. Maybe you could dedicate more time for the search for life. When we look at future technology, we find more evidence of looking at the same stuff, but at better resolutions. However, there's some ambitious projects that will open up new horizons. The ELT is an ambitious project that will open up new horizons for astronomy. The ELT will be able to study some of the most challenging and fascinating phenomena in the universe, such as the formation and evolution of galaxies, stars, and planets, the nature of dark matter and dark energy, and, at the very last, the origin of life. The good news is ELT will be able to observe some of the exoplanets found by TESS and James Webb and look for biosignatures in their atmosphere. It will also be able to search for new exoplanets using different techniques such as direct imaging, radial velocity, and microlensing. It would also be able to test fundamental physics and cosmology by measuring the properties of black holes, neutron stars, and gravitational waves. And if you follow astronomy, you'll find that, of course, the bulk of what is given for the ELT to look at will be black holes and neutron stars, the favorite shiny objects of astronomers that they love to stare at for decades. While I'm sure it's beneficial to study these phenomena, I wonder in what way does the prioritizing of these over the search for life make any real sense. That being said, there are some future telescopes and observatories that show some promise. The HAB-X, the Habitable Exoplanet Observatory, the Large UV Optical IR Surveyor, or LUVOIR, the Origins Space Telescope, the Lynn X-ray Observatory, the Planetary Transits and Oscillations of Stars, or PLATO, the Atmospheric Remote Sensing Infrared Exoplanet Large Survey, or ARIEL. These new telescopes offer some hope in this desire to find life. But again, it will be successful in so much as scientists want to actually find life. And at this point of the story, I don't know if they do, for whatever reason. Maybe some form of microbial life form they're okay with, but not actual intelligence. Is this merely because they're afraid of the social stigma they think surrounds the topic of aliens? Or is it something more? Scientists always complain about funding. And I think about how fundamentally our own world would be changed from the knowledge of another intelligent species out there on another planet. Everything would change. And it would reverberate throughout all the sciences. And ultimately, this is what I think the reason is. Instead of thinking this would expand their funding for observation and discovery, they think of it as they're being too comfortable in their fields. They've spent too much time on their work that finding life would be a threat to everything they've built. And much like the field of archaeology, it blinds them and stunts their curiosity. So in all likelihood, we will be staring at black holes and talking about dark matter for another 40 years, if something doesn't wipe us out before then. But what do you think? Do you think the scientists want to find life, or do you think that there's other reasons they don't search for it as rigorously as they should? Let me know in the comments below. Please like, share, and subscribe. It really helps out a small channel. And thank you so much for watching. I'll talk to you next time.